So, hi guys, welcome to Bookmasters Academy. I'm really excited to be here. My name is Uncle Stanley. To get more details about Bookmasters Academy or myself, you can go to the channel description. You can go also to the profile picture of the channel to get more information about myself. Okay, without wasting time, we'll be going straight to business. And our topic for today is dimension. And during the course of this interaction or during the course of this teaching, uh, I'll be teaching dimensions for beginners, for intermediate, and also for advanced learners. Maybe in subsequent videos, we're going to throw more light on this. But with this video, you're going to get a good grasp of what dimension in physics is all about. So I won't forget to mention uh, the science lovers too, who just wants to know about science and what's going on in the environment around them. You're going to find this video very interesting. Okay, so diving straight to a specific objective or what to expect in this video. Okay, in this video, you'll be expecting you expect to get a very good understanding of dimension, okay? Not just at the surface level, but we'll try to break it down so you know what it actually means. Okay, so we'll also be putting a lot of JAMB and a lot of questions that are potential questions for external exams and all. So in chapter 2, we're going to be seeing the applications of dimension, where we'll look at how dimension is used to verify physical equations. Come on, in physics, you have so many physical equations. So people are deriving new ones every time. You have loads of physical equations. So you really want to make sure that these equations are correct, because any equation that is not dimensionally correct, it's wrong. It's not a good equation. So we want to know how we do this. We also want to know how to derive unit, because without unit in physics, physics is what unit is what makes physics special. So you can't solve and you don't tell us your unit. It doesn't make sense. This is not mathematics. You need to put your unit right there. So if it's a dimensionless quantity, if it doesn't have unit, then we would know. But if it has, you must put it. So you must dimension helps us to derive unit. We're going to see how to do that. Then this is the most favorite part that you just don't want to miss, especially for those preparing for various external exams in science. I would urge you to stick to the end. And the most exciting part is our quiz. We'll be dropping quiz for you guys to try out and drop your answers in the comment section. And believe me, there will be juicy rewards for those who do that. So without further ado, let's dive straight to business and get our hands dirty. Okay. So understanding dimension, okay. Another word for dimension is dimension analysis. Okay, so what is dimensional analysis? Dimensional analysis is a powerful technique in physics that connects physical quantities to fundamental quantities. Okay, one would say this is a whole lot. Let's break this down very, very well for you. I don't know where you're watching from, but if you just take a moment to wonder, what's my height? What's my weight? What's my mass? Come on, all these attributes are quantities in physics. In physics, we refer to these things I mentioned as physical quantities. Generally, in physics, we deal a lot with quantities. Like, quantities are so important. So, because this helps us to take measurements in the environment. Quantities are all around us. So, ranging from simple quantities or what we say basic quantities, like fundamental quantities, because every science students, when you just enter into science, we try to introduce you to these things. We try to tell you, you must know your fundamental quantities. These are basic quantities that we cannot break down into simpler ones, like in their simplest form. So we are talking about mass, we're talking about length, we're talking about time, we're talking about electric current. We mentioned thermodynamic temperature or temperature. We also mentioned amount of substance and luminous intensity. So these 7 quantities are referred to as fundamental quantities in physics. So these are the basic ones, like very, very simple ones, like basic ones. So anything you're talking about that is not these ones are referred to as complex or derived. So the right word for it is derived. So you now start to mention velocity, you start to mention speed, you mention force, you mention energy, you mention pressure, work done, you mentioned power. All these things are the derived ones. Okay, these are quantities. We're still talking about quantities right here. So we talked about quantities, and we talked about the fundamental, talked about the derived. Okay, so where does dimension come in? Where does it come in? Okay, now let's take this, let's picture this. Take this. If we want to talk about power now, power as a physical quantity. Now, if you want to refer to power as a physical quantity, you can say in physics, okay, power is, because in physics we talk about formulas a lot. Say, okay, power is work done over time. One of the formulas we have is that power is work done over time. Okay. Now, the problem is that work done is force times distance. And you have force times distance over time. And force is mass times acceleration. You see now, everything is getting complex. We started from power to be work done over time, and we're taking it down to work done is now force times distance. Now that force is mass times. Oh God, this is the whole lot. So, well, that means power must be something crazy. That means power is just a large and complex thing. It's too complex. You see? So at this point, that's where we now bring it down to dimension. Dimension, in the world of dimension, we don't care who you are. We don't care. It's either you are M, it's either you are L, or it's either you're T. So most of the physics quantities, if not all, can be broken down. If you step it down, guys, you can step it down to the dimension. Once you step it down to dimension, you will not see any other thing than MLT. MLT. And you remember, guys, MLT, okay, mass, length, and time are members of the fundamental quantities. So we can bring down any physical quantity. Let me make a pointer. We can bring down any physical quantity. Okay, so we can break down any physical quantity to the fundamental quantity. We can break down any physical quantity to the fundamental. So let me define it again right now. So dimension analysis is a powerful technique in physics that connects physical quantities to fundamental quantities. So we try to bring down any physical quantity and we try to take it down to the fundamental quantities. And in dimension, the most important fundamental quantities that we talk about are mass, length, and time. Mass, length, and time. So, and when you talk about mass, we don't even, dimension is just too sweet. We don't need to write mass. No. In dimension, we just refer to mass as M, M, M. Then we refer to, M. We refer to length as L. You see me, I try to put it in blue, the font in blue, and you have your time, you refer to it as T. So that's dimension for you. We don't like stress. So another thing I try to point out here is that the unit for mass is kg. So let's say you want to get the dimensions and from the units. For instance, they gave you some units and you want to get the dimension from the unit. So if you see kg, you just know that the dimension is m. If you see m, that's meter, kg, kilogram. So this is m. So if you see meter, that means the dimension is length, L. Then if you see S, which stands for seconds, that means the dimension is T. So this M, this S, this kg, all this is a unit. So in case you're getting it from the unit, fine, you can get your dimension from the units. That is actually nice. And I always advise beginners to get your dimension from the unit. So if you get your unit, if you know your unit, you can get your dimensions. But as you proceed, as you grow, you may even just look at the quantity and know your dimension. Come on, can't be doing that derivation every time. Okay, so now we try to get a very good grasp of what dimension is. So let's now go down. This method helps us to understand the underlying structure of physical quantities. This method helps us to understand the underlying structure of physical quantities. Okay, let me give you an example. Let me give you an example. Okay, let me go to my second slide. Let's go. Okay, this is my third slide. So this is pressure. This is pressure. So you see, pressure, this is the dimension MLT. Velocity, this is the dimension LT. And viscosity, you will not see anything that is not M or L or T. You will not find that in dimension. No matter how complex, no matter how big the formula is, it's always M, L, T, or just M, or just L, or just T, or a combination of two or more. So if you see a pressure, you see all these things, you can, once you step it down, trying to step it down, I will now have a dimension. So that's exactly what I'm talking about. So let's go back to our slide. Okay, guys, having said these things, let's go down to some specific examples like velocity. Velocity, okay, let me just say some things about velocity. Velocity is a vector quantity. That means it has magnitude and direction. Okay, so everything, you have your acceleration to vector quantity. So let's go down now. Velocity, as an example, is the formula for velocity is that velocity is displacement over time. That is displacement divided by time. Displacement is the distance traveled in a given direction. Okay, so if you travel a particular distance and you tell us your direction, you call that displacement. But if you just travel a given distance, you just call it distance. Okay. Um, the unit for displacement is the same thing as distance traveled. So distance traveled, the unit is meter. So you want to tell somebody I've traveled, you can tell somebody kilometer, but no. The SI unit is meter. So now you can see. So and it's the same thing as displacement. We don't talk about the direction so much in this scenario. So we have the unit to be meter divided by seconds. So we're trying to get the unit. So I told you for beginners, you can get your dimension from your unit. Yes, it's usually sweet. And if you're just coming into science new, a new person in science, it's always not advisable to get it from the unit. But as you proceed, may not necessarily need to do that anymore. So time is seconds. So we have meter by seconds. That is meter slash seconds. So that's your that's this being expressed mathematically like this, or you can just do meter seconds raised to power minus one. Minus one means that you're going down. You're going down, bro. You're going down. So dimension. So what's the dimension? The dimension is, since we've gotten the unit, so we'll just put this meter, just like I said here, the unit. Told you this M is for unit, this S is for unit, this kg is for unit. So this T is for dimension, this big L is for dimension, this one is for dimension. So let's see. Now that we have our M as a unit, it will turn to L. M as a unit, it will turn to L. So our dimension is L divided by second as a unit, we turn to T. Second as a unit, we turn to T. And now we have LT raised to power minus 1, just as you have MS raised to power minus 1. So I didn't want to write it like this. It's just stress. So notice that M does not appear since velocity does not depend on it directly. So you see, guys, you may not have ML, you may not have the whole MLT. You may just have LT, you may just have MT, you may just have LT, just like we have here. You must not have all three. So that's just the point of this whole right up here. Okay. Let's go. So for acceleration, we have velocity over time. So that's what acceleration basically means, guys. So acceleration is velocity over time. So let's go to the unit. We already derived the unit for velocity. So that's the sweet part. So we just go here and pluck it out. So pluck it out is m over s. So if you divide this by s, imagine something having a numerator as m and a denominator as s, and you now want to divide it. When you divide something, you take it down to the denominator. The division, when you divide something, the divisor usually goes to denominator. So this guy goes down and it adds up. It adds up to make it m/s squared. So you see, what you have here now is m/s squared. Or mathematically, you can have it like this: m um, per second square. That is meter per second square. That's what we'll call it, per second square. So this is seconds. You have per minus then square 2, so meter per second square. So it makes sense. Okay, now dimension. For dimension, what can we do? What can we do? Okay, so we have our LT raised to power minus 2. How did we get minus 1? So I told you this is just a representation of this m/s. It's just like saying we brought our unit as m, and now we have our dimension as L. We brought our unit as S. We have a dimension as, so instead of writing it L/T, just L/T. Instead of having L/T, I decided to write LT raised to power minus 1. So this is the dimension for this. This is the dimension for this. Now this one is just basically this. Okay. I think there's a mistake there. Okay, I forgot to put, it's supposed to be an m. I'm going to be adding it. Yes. So this is it, guys. Okay. Let's go to density real quick. Density, just real quick, density is a scalar quantity, and unlike acceleration and velocity, displacement, this one is scalar. This one has only magnitude. It doesn't have direction. So that's that for that. Density as a physical quantity is mass over area, mass over volume. Sorry, mass over volume. Okay, so what's the unit for mass? We have our units to be, let me put on my pointer. So we have a unit to be kg divided by volume. Volume is length times breadth times width, but we don't really care about breadth. We don't really care about width here. All we care about is length. So we're going to make the length 3 times length times length, so that we have our unit to be meter cube. So I've said it, the most important fundamental quantities here are mass, length, and time. So everything comes down to length. Not in as much as you're dealing with something related to length, it will change to length automatically. So okay, so that's that. Then we have a meter cube. Now when you multiply, okay, when you divide this, you have kg all over meter cube. So if you don't want this slash here, you can just turn it to minus. Okay, so this will be kg per meter cube. So there should be minus, skipped. Okay, so it's not skipped here. So let's proceed. So for the dimension, you have kg. Kg, I told you, when you see your kg, just know you're dealing with m. That's mass. So when you see your kg, you change it to m, and when you see your m, you change it to L. So that's it right there. You change it to L, and what do? You finalize, and you get this. So we're getting our dimensions of our various physical quantities, and we're doing that very, very easily. You see, guys, for dimension, the most fundamental quantities, the most important fundamental quantities I will talk about is the mass, the length, and the time. These are the ones we don't joke with. Okay, so MLT. So key rule: physical quantities can only be added when they have the same dimension. You cannot meaningfully add area to speed. That's weird. You don't add area to speed because they don't have the same dimension. They don't have the same dimension. So in any equation, P is equal to A plus B. For any equation such as this, all terms must share identical dimension. Okay, this means that if P doesn't have the same dimension as A, it's not possible. You can't even have this. It's not even possible. This equation is wrong. I'm going to be saying that you can't have it. It's not possible. So that's how it works. So all of them, this must have the same dimension as this must have the same dimension as this. So if you bring an equation, if they ask you in JAMB, is it an equation dimensionally correct or is this equation correct? All you just need to do is to step it down to dimension. Just step it down to dimension, guys. Once you step it down to dimension and they all don't have the same dimension, that means that is wrong. That equation is 100% wrong. It's all wrong. All wrong. Okay, so tensile stress, tensile strain rather, is increase in length per unit length. This is a JAMB question. It's a JAMB question. It comes out. So you need to know your dimensionless quantities. Like tensile stress is one of them. Tensile strain is one of them. Not tensile stress, rather tensile strain. So tensile strain is increase in length all over original length. So it will just be like length over um uh extension over length. Some people just say it's extension. Yes. So increase in length is actually extension, obviously. So is that the right thing to say? Okay, this is not wrong, but this is the same thing as extension. So extension over original length. So it's dimensionless because basically, if you get extension, what's the unit for extension? Is meter. As I told you, we recognize all these things as distance traveled. So whether your height, everything. So extension is meter, length is meter. So their dimensions are L over L. So they will cancel out and there will be no dimension. So you have both numerator and denominator have dimension L. This will cancel out. There is no dimension for strain. So let's go down to application, guys. Okay, let me go back. Applications of dimension. Okay, so the first application that we're going to be talking about is verification of physical quantities. So we use dimension to verify physical quantities. And how do we do this? So one of the most practical application of dimension is verifying the correctness. And they can give you 2 to 3 equations that are wrong and just one is correct. You need to pick the correct one and you can use dimension to figure this out. Let's check this out, guys. Example, equation of motion. Okay, so this is one of the equations of motion. Among the others, we have others. So a student needs to verify if this equation is correct. So I try to put out a couple of steps that we can use in dimensional analysis, and they include just first thing you need to do is to analyze each term. So this is a term. UT is a term. Half AT squared is a term. So S is a term. UT. Okay, so let's analyze each term. So break down the term into individual components, blah, blah. Okay, so let's see. Analyze each term. So when we look at each term, what can you make out of it? So the first term is displacement. This S is displacement. S is displacement. Displacement is X. So S. So we have dimension of S is L. So I told you displacement is the same thing as distance. It's just that it's a distance traveling in a given direction. But we don't take cognizance of the direction in most cases, except we're dealing with vector proper. That's where we'll deal with the direction very, very well. So, but in this case, we don't talk about the direction. So, if that is the case, we will just see that the dimension for displacement is length. L. So, this is it. The unit is meter, obviously, but the dimension is L. We talked about this in the former slide, where velocity is displacement over time. Can go back or rewind, we come back to this point. So we now know that our left-hand side, the bone of contention is the dimension is L. The dimension for this guy is L. So let's check this whole thing. Does it combine to give us L? If it doesn't combine to give us L, guys, it's out. This equation is automatically wrong. We don't even need to go further anymore. So let's go. Check first term, UT. Okay, just to make sure we are clear. U is velocity, but it's initial velocity. V is final velocity. U is initial velocity. V, final, U is initial. So all we know is this is velocity. And we already know the dimension for velocity in our former slide as LT raised to the power minus 1. So if I multiply this with T, this guy will cancel this guy. So this guy is just like 1 over T. Just because of this minus, it's like 1 over T. So when you multiply, you just have L. So you see, this part is correct. So this part is correct. Let's take the final part. So when you're doing dimension and you have this coefficient of numbers, you just tend to ignore it. It's of no use. It's not going to do anything. So when you're doing your dimension, you can just behave as if I didn't see this. So let's go. The dimension for half AT squared. A is acceleration. T is time. So let's see. So dimension for acceleration, we already saw it in our former slide, is LT raised to power minus 2, guys. So when you do this A is LT raised to power minus 2, then times T squared. Time, this is A times time, acceleration times time. So this is acceleration times time squared. So the dimension for time is T, capital letter T. So when you multiply this 2 minus 2 times T raised to power minus 2 and T raised to power 2. These guys will cancel. You have so hooray, this is correct. This question is very, very correct. Now, this verification process ensures that physical equations make mathematical and physical sense before applying them to solve problems. So you don't just dive into an equation and start. So we don't just introduce an equation to me and you want me to start using it to solve wave problems or heat capacity problems. Guys, you must test your equations to be sure the dimension is correct before you proceed. So moving down to the next application. So the next application, guys, is deriving units. Deriving units. Okay. So in this part of this video, we're going to see how we can use dimension to derive units. So remember during the part of this beginning of this video, I said that if you want to get dimension, the easiest way is to use units. So you get the unit, let's say you get a unit as kg, you just write the dimension as capital letter M. You get it unit as lead meter, you change you write it in dimension as L, capital letter L. So now we want to do reverse, and that's how we use dimension to get the units, because we first of all we get our formula, then we get our formula for the quantity, then we'll now break it down to dimension, then we'll be able to just pluck it out. This is this, this is this, this is this, as easy as that. So let's just say this is very, very simple. Okay, so let's dive to velocity, velocity unit. So we want to get the the unit for velocity as a quantity. So velocity is a quantity, a physical quantity. So we want to derive the unit. So velocity is displacement divided by time. Displacement, we have talked about it so much. We said that it can be seen as a length. Yes, in dimension, we see it as length, even though it's a distance traveled in a given direction. But here, we don't talk so much about that. We just say it's a length. So we write as L, time is T, capital letter T. That's how we get it. So the dimension now is, so we got the formula first, we got the dimension. The dimension is this LT raised to the power minus 1. So now that we know that our dimension is L, the unit is for L, which is length, which stands for length. The unit is meter and T is seconds, so meter per second. So we got our unit from our dimension. Okay, so let's do for pressure. So pressure as a physical quantity is seen as force over area. So force on its own is mass times acceleration. So we haven't talked about this, but force is mass times acceleration. Area is, okay, we'll break down area in the next formula. So area is length times breadth, but basically in this topic, we don't bother so much about so many things. We'll just take it down to length times length. So that's it, because breadth is a type of length. Good. So that just has displacement is a type of length as well. That is if you are not considering the distance or the direction rather. So you have your mass, but acceleration is velocity over time. And you know, velocity over time is something as velocity divided by time. So, but in mathematics, okay, if you want to convert this to dimension, now length is length, L is L, breadth is length. So, because we don't have breadth in dimension, what we have is length. Now, mass is mass, then velocity on its own is L over T. That is L over T. We've seen it, okay, we've seen it already. That is this L over T, this is L over T. In other words, so this is velocity, this is velocity, this is velocity, this is dimension. okay, this is it, this is it. Now, what about this time? This time you have L over T divided by T. But in mathematics, if you have divided by T and you want to turn it to multiplication, just turn it upside down. The division sign, we turn to multiplication sign. So instead of having this divided by T, we just turn it upside down. So we'll have multiplication. So having this now, just see what I did here. Now, this T and T that are under, normally in mathematics, they'll just step down, they'll just come down and join this, their brother here, LL. They'll just join that. So you have L times T in the denominator side. That's the normal thing to do. So in the numerator, you just have L and M. So, but I didn't want to get this place all jungled up. So what I just did is this. I just left it like this. So we'll have TT in, just have it in that in your mind, at the back of your mind. So what we'll do now is one of these L will cancel the L that is up, because that's what is up now, just L and M. So if it cancels out, you just have one L surviving. So that's this L. M, there is no complication with M, so it's still there. So what else do we have? What else do we have? Remember, we still have our 2T under, nothing has happened to it. So because of all that, so we just brought it here. C raised to power minus 1. That's that for that. We now have M. Capital letter M is mass. So what's the unit for mass? Kindly, it's kg. We've gotten our unit. L is M raised to power minus 1. T is, that's just it. Hooray. So we got that one. Now, for pressure, we usually do something. We usually have an SI unit in physics. So this is not usually derived. This is different from the derived unit. The derived unit is this. The SI unit is this. So the SI unit is just obtained from the formula. Newton is the unit, SI unit for force, and meter per meter is the SI unit for this. So don't just confuse yourself about this. It's actually a very simple thing. So you have your Newton for the SI unit. The standard international unit for force is Newton, and the standard international unit for area is meter squared, but because area is under, it's now meter raised to power minus 2. So we have viscosity. Viscosity is basically force over area times velocity gradient. So what is velocity gradient? Velocity gradient is velocity over distance. So that's what velocity gradient is. So we have, you see, this is looking complex, but still very, very simple. So we're going to break velocity down. So we'll have velocity is displacement over time. Now, just as we did here, that we got velocity to be this displacement over time. This distance is going to, instead of just dividing this with this, so turn it upside down, so that distance would come under. So exactly what we did here. So we had this L over T, then it's supposed to be T, because velocity is this. So instead of dividing, we just turn it upside down. So that's what we did here. We have velocity to be displacement of time. We brought this and tumble it, and we have this. So there is a tumbling going on here. So at the top part, we just have force and mass over mass. So breaking this down into dimension, we have mass as the dimension as this. Acceleration is velocity over time. Velocity over time. Just exactly what we have here. Just exactly what we did here. So instead of doing this again, we just plug this. Just plug all this. So this is it. This is it. So basically, this is force, with mass and acceleration. I just plucked out everything here, and I have this. So for the denominator part, which is the part that is slightly new, we have displacement, which is L. We have time, which is T. We have 1 over distance, which is still L. So what do we do here? I'd always tell you, this T will just come down. Yes, everything at this T will come down. But I've not told you about when you have a fraction in the denominator. When you have a fraction in the denominator, what happens to the denominator of the fraction is that they will go up. So for numerator, when you have a fraction, the denominators will just come down. But you see, when you have a fraction in the denominator would go up. So if you want to just have a single fraction, so then naturally, for you to make all these things to be just A over B, these things I'm saying have to happen. So they have to happen. You have so you what you have is that this T and L would go up, and this TT would come down. So what you now have is you have TT under here. Then when you have TT under and you have T on top, so you discover that this T that is on top and TT under, they would cancel out.
So you have TT under, you have this T that will go up. So one T would cancel one T so that you have just this second T here. That's why you have a T that survived. Now for the L part, we have L. This L will still be retained at the top. Now this L will be retained at the bottom. So they would cancel out. Now this one, okay, if you don't want, you can just cancel out L. Yes, instead of taking L, but let's just continue. So we say that these two are up. So now that you have this L to be up, it will just cancel out this L that is down. So you're having L to cancel L. This L will cancel out this M. L eventually. This yes, yeah, and this L will cancel out this L. Now you have this T going up, while these two T coming down. So this one of the T's that are down will cancel out one T that is up. Then you discover, I told you that's why you have your T minus 1. So your L is just remaining 1 as well, because I told you this L that is up will cancel out this L that is down. Okay, this L that is up will cancel this L that is down. Why this L that somersaults up will cancel out this L. So you just have only one L and you have one M. So at the end of the day, this is what you have, and this is your unit. And how do you do that? You have your M as kg, you have your L as meter, you have your T as seconds. So that's just it. I say again, these two T will come down, T would go up. So eventually, if these two T's are coming down, so and this one is going up, so you can cancel this T that went up will cancel the one that went down. So you just have only one T surviving. That's that. Then remember, an L went up and there is an L off. So that this L that is up will remain. So this L will cancel this L. This L that is up will cancel this L. So you have only one L remaining. So your M is still there. So this systematic approach ensures consistency across all physical measurements and helps scientists to communicate precisely about quantities regardless of specific unit system used. So whether you're talking about standard units, we can just work with the derived unit, and all of us in different part of the world will still be having the same thing. So the final part is how we use dimension to relate to get the relationship between physical quantities, and that's where you should be very, very careful about. So I'm switching screen for this part. Welcome to the third part of applications of dimension. This is actually my most favorite part, and the part where you should be very, very careful about, because this is the part where a lot of students usually get it wrong. A lot of students. But if you stick around, pay focus, and you're going to get the full details, and you won't be missing anything. So let's get our hands dirty right now. So this is going to be our first question. So I'll label it number 1. Now I'll rule my line just in case. Okay, now let's go. Okay, so in this part, we're trying to use dimension to derive the exact form, or the exact form of the relationship between physical quantities. So we are meant to understand that physical quantities have relationship. There's a way they relate in various forms. Yes. So they relate in various forms depending on what you're doing at that particular point in time. So if you want to relate work done, you can relate work done with force, you can relate work done with power, you can do a lot of relationship, you can do a lot of relation in physics. So if you're not careful, you're going to get it wrong. So what dimension does is this: it helps us to get the exact form. So if you are not in line, you can use dimension analysis to be sure that this is actually the exact form of relationship. Even if you don't even know how they relate, dimension analysis can help you to know the way they relate. And that's what we're going to do here. We don't know how period relates with mass. I'm going to be underlining it. We don't know how period relates with mass and relates with length. Yes, as well as acceleration due to gravity. So we want to check how period, which is t, relates with mass, relates with length. This is supposed to be L. Let me just put that L. So relates with length, relates also with G. So we want to see the relationship between period, mass, length, and gravity. So this is actually a very interesting one. So the first and foremost thing, the first thing that we should do at this point is to introduce some nice exponents. Some nice exponents that were not there before. So we're going to be introducing. So let me just try to introduce instead of A, B, C, let me introduce X. I'll use the next as Y. Then I'll use the next as Z. So I'm introducing X, Y, and Z as my exponents. So after doing that, we'll see the reason for doing this real quick very soon. So at this point, what we're going to do now is that since we're trying to relate period with mass, length, and acceleration due to gravity, we want to get the relationship, how period varies with this. So I'm going to introduce our proportionality sign, which is a normal thing when studying variation. If you've done your partial variation, direct variation, and joint variation, this shouldn't be a new thing. So after introducing my proportionality sign, the next thing to do normally in mathematics is that you want to remove this proportionality sign. You want it to be an equality sign. So for you to do that, you're going to write your equality sign fine and good. But the problem is that if you introduce an equality sign, you must put your k, guys, like you must introduce your k. So if you do that, you're going to now have the equation to look like this. C, which is period, is equal to k, which is a constant. So dimensionless constant, that's what we call it, dimensionless. It doesn't have a dimension. Any constant you put here doesn't have unit, doesn't have dimension. So the constants that you introduce doesn't have unit, doesn't have dimension. So that's that. Now I'm going to be writing my other variables just as they were before. So just do this, do this, do this. So now I have my X, Y, Z. So what's the next thing I'm going to do? At this point, I'm going to break each of these variables down. I'll break each of these variables down into their dimensions. So remember, we're trying to get the exact form of how quantities relate, and we're meant to use dimensional analysis. So now we have all these quantities and they're just all over the place. We want to break them down into dimensions so we can go ahead from there. So what we're going to do now is that period in physics, period is the time taken to make one complete oscillation. So time, emphasis on time, guys, emphasis on time. So the dimension for time is t. So I'm going to write t here because that's the dimension for time. I told you the next step is to convert everything into the dimensions. So we're going to write equal to k is dimensionless. K is dimensionless, guys. So I'm going to leave k as k. Now m, the dimension for m, that is mass. The dimension is still mass, guys. Dimension is still m. Sorry, the dimension is still m. So I'm going to be writing, maintain my m. Now, the dimension for length is L. Very good. So I will still maintain my, even though this L, yes, this L is length. So yes, we're on track. So now the only complicated thing is the G. So G, we have seen G in our initial question. Let's take a look at what I'm talking about. Think in slide 2. Yes, let's look at it. So, as you can see, the dimension for G is actually LC raised to power minus 2. So it's obvious the dimension for G is LC raised to power minus 2. So that's G is acceleration. It's simple, it's acceleration. So I just went back so that we can see what acceleration is. So here we're treating acceleration as so we're treating G as acceleration, and that's what it is actually. Because if you come back to the question, you can see, if you come back to this question, you see acceleration due to gravity is G. So acceleration is the point of interest. So acceleration is the point of interest. So that is to say, our G would be having a dimension of L C raised to power minus 2. So our dimension for G is LT raised to power minus 2. guys. So that's that. So we have the dimension for G. So I'm going to write it line, write that as LT raised to power minus. We have a dimension for G. We have a dimension for L. We have a dimension for M. We have all our dimensions in place right here. So what's the next step we should take? So the next step now is, first of all, I like to simplify. So let me just put this down. Dimension here, dimension at this point is dimension. Then before that, we didn't do anything. We just introduce a constant, introduce our constant. Yes, that's what we did. Then the next step is to simplify. I like to simplify, guys. I like to simplify at this point. So what do we mean by simplify? We have K, then you discover that you have L here and you have L here. So I will try to make L to just be a 1. Just make L to be 1. So that if we're looking for L, we just look at it as 1 spot. We don't be looking for L, 2 spots. So here we need to apply some laws of indices, some nice laws of indices. So what we're going to do here now is that we'll try to expand this. And see what we can make out of it. So we'll try to expand that, guys. So let's see. The law of indices will tell us that LT raised to power minus 2z can be written as LZ T minus 2z. So basically, we use L to times this, and we use T to times this. So we're now having LZ, L with times the Z. So everything is multiplying the exponent outside the bracket. So L times Z, T times T raised to power minus 2 times Z. So we have our final answer to be LZ T raised to power minus 2Z. So that's what we have right here. So we're going to use this, and we'll bring it, we'll bring that knowledge back. We'll just keep it, let's just keep it close yet. Let's just keep it close for now. So what we have is LZ T raised to power minus 2Z. So we have this very close. Now we're going to use this to multiply our L Y. We're going to use this to multiply our Ly. Yes. So we're going to use it to multiply Ly. See, that's where we now apply the second law of indices, guys. So the second law of indices will tell you that the second law of indices that will apply here, but actually is the first law if you're to use it properly. So if you do a raised to power 2 times a raised to power 3, guys, your answer will be a raised to power 5. I presume you guessed right. Okay, so if that's the case, so we're going to, this our a now is seen as L, this our second a is seen as L. So in this case, we're going to have L, which is our a, which was our a. We're going to have L raised to power z plus, or let's write y first. Y should come before z. Let me just, addition is commutative, so that's not a problem, but then just do it right. So this is what we have. Then we now have t. We now have t raised to power minus 2z. So what do we try to do? We try to see how we can simplify the L, because I have L in 2 places and that's not fresh, that's not nice. So we try to make it together. So at this point, our new equation is now T is equal to this. Then I have my M, I have my raised to power Z, X, I have L raised to power Y plus Z. Then I have T raised to power minus 2Z. So that's what I have right here. So next thing I would like to do is to equate the powers. We're going to equate the powers. So equate the powers. And I'll tell you what I mean by equate the powers now. Equate the powers or equate the exponents. But exponents. So if you notice, you see that there is a t in the left-hand side of the equation and there's a t in the right-hand side of the equation. So because of that, a lot of things are obtainable at this point. So we'll be able to get our exponent that we introduced. We're able to get the value for x, we get the value for y, we get the value for z. So let's just do that. Let's just do that real quick. So how do we get the values for x, y, and z? First of all, you need to know that there is an m here, but it's raised to power 0. That's why it's invisible. It's invisible because anything raised to power 0 is 1. So there is an L here too. It's raised to power 0. So the only thing that is visible here is t because it's raised to power 1. So for to start with, or it's advisable to start with the power that is single, because the work is going to be very easy. If it exists, you work with the one that is single. Let me show you what I mean by that. So we'll be working with x. So we want to find x, y, and z. We want to equate it, the powers in the left-hand side to the ones in the right-hand side. So, but in this case, we're going to consider x because it's single. The next one, y plus z is not, that of z is not. So we can start with anyone actually, but I prefer to start with the one that is single. So and just make this a little bit what I just wrote down. Okay, so if we do this, we'll have m raised to power 0 is equals to m raised to power x. So a lot of indices will tell you that the bases will cancel. You have 0 is equals to x. So x is equal to 0. So we have x is equals to 0, guys. So that's that for x. So the next one would likely be looking out for is we'll be looking out for, let's just go to the next one, obviously. So if you go to y plus z, okay, let me not write it like that. Let me just do as I did in the former case. Okay, let me just clean this. Okay. Okay, so if we want to do for the next now, we're going to write that L raised to power 0 is equal to L raised to power y plus z. So this is what we'll have right here. So we can equate the powers. We cancel the base and equate the power. So we have 0 is equal to y plus z. So this is what we have. You can't have two unknowns in an equation except it's a simultaneous equation, which is, I don't think this is one. Yes, this is not it. So, but we can actually do something. But for now, let's just leave that. Let's just leave this for now. We can call this, if you like, can call it equation 2, but I feel like that's not necessary for now. Let's just continue. So, the next thing we're going to equate now is going to be equating t raised to power 1 with, because I told you the t has raised to power 1 and the t raised to power minus 2z. So the one I'm talking about is here. So we'll cancel the base. We'll have 1 is equal to minus 2z. So therefore z is equal to minus 1 over 2. So z is equals to minus 1 over 2. So if z is equals to minus 1 over 2, we can put the value of z, into, okay, let's just call this equation 1, equation 2, then this is equation 3. So put the value of z into equation 2. If you do that, see what you now have. You have 0 is equal to y plus bracket minus half. Good. So at this junction, you can just take this to the other side so that you can have half is equal to y. Good. So our y is half, while our z is minus half, guys. So let me just highlight everything that we've gotten so far. We got our x to be 0. We got our y to be half. We got our z to be minus half. So we got our z to be minus half. So having gotten these three things, these three values for our exponents, we can now put into the equation with the constant. The equation with the constant, not the one that has the dimensions, rather the equations that has quantities and constants. So I'm going to circle it here. So this is the one I'm talking about. So that's the one I'm talking about. I'm going to be putting an asterisk here. I'll clean every other thing and leave that one. So that's where we'll be continuing from now. At this point, we just need to impute our variables, our exponent that we got. We'll impute it into the relationship that we've obtained. The relationship is this. This is our relationship. This is our equation that was formed from nowhere. We just derived it using dimensional method of dimension or dimensional analysis, and we're able to get our equation that is exact, that is true. So that's the essence of using dimension. So what we're going to do now is we're going to put the values. So we have our t is equal to k m raised to power 0, l raised to power half, and g raised to power minus half. So law of indices will tell you that any t raised to power half is going to put that thing inside the root. So have anything raised to power half would have a square root. Then this minus sign here will just tell you that you're going to have a square root, but this time around it will be in the denominator. So see what I mean? You're going to have g. So what I'm going to do here now is m raised to power 0 is 1, so it will disappear. So we'll not have m again. So for this l raised to power half, it will cause a square root like this. Good. Then for g raised to power minus half, you have g to be under. So you can just decide to extend this so that we'll have something that looks like this, and we are done. We are done with everything. So this is the relationship between t, then l, and g. K is a constant, so we don't talk about it. So it's a relationship between t, l, and g. Okay guys, that's been a very good section, and to wrap up this section, we'll be dropping a Bookmaster quiz. Surely there will be awards. So what are you expected to do? Expected to obtain the dimensions. Expected to obtain the dimensions for Young modulus, universal gravitational constant, and surface tension. Drop your answer in the chat box. We'll give you further instructions. Once we're able to confirm and verify that you did it yourself, you would receive your award. Okay, this is going to be for the first 5 persons that would do this and give us feedback. So thank you very much. Remember to like and subscribe to our channel to get more of these kind of educative videos. So thank you.